Hello. Today we'll present our project modeling a quadrotor as a differentially flat system and planning feasible trajectories. Our goal is to generate smooth, collision-free, and dynamically feasible trajectories for a quadrotor in 3D environments. Here is the structure of this presentation. First, we define the problem and explain why differential flatness is useful for quadrotor trajectory generation. Then we introduce the overall planning strategy from A-star path search to quintic trajectory generation and Newton-based optimization. Finally, we show applications to different environments followed by an ablation study and conclusion. Differential flatness means that the full state and control inputs of a system can be represented by using a small set of flat outputs and their derivatives. For a quadrotor, instead of directly planning in full dynamic state space, we can plan using position and yaw. This reduces the planning dimension and makes trajectory generation faster, smoother, and more suitable for control. For the quadrotor, the flat outputs are x, y, z, position, and yaw angle. From these four variables and their time derivatives, we can recover the full position, velocity, attitude, angular velocity, thrust, and torque. So the trajectory can be planned in a lower dimensional space while still being dynamically meaningful. We begin with the translational equation of motion. The mass times acceleration is equal to the gravity term plus the thrust direction term. Here, R is the rotation matrix from the body frame to the world frame, and the F is the collective thrust that generated by the rotors. By rearranging the translation of dynamics, we define the acceleration command. This acceleration command is the desired translational acceleration plus the gravity compensation term. In other words, it represents the acceleration direction that the quadrotor must generate through thrust. So from this equation, the body z-axis is aligned with the acceleration command. Therefore, the thrust direction is determined by the direction of this vector, and the thrust magnitude is determined by its norm multiplied by the mass. However, the body z-axis alone does not fully determine the attitude of the quadrotor. There is still one remaining degree of freedom, rotation around the body z-axis, which is yaw. This is why yaw angle must be included as one of the flat outputs. Using the yaw angle, we define the desired heading vector. Then, together with the body z-axis, we reconstruct the remaining body axes, B1 and B2. This allows us to build a complete orthonormal body frame. By stacking B1, 2, and 3 as columns, we recover the desired attitude matrix R. This means that the attitude can be computed from the second derivative of the position and the yaw angle. Next, angular velocity is recovered from the time derivative of the rotation matrix. Since the rotation matrix depends on the acceleration and yaw, angular velocity depends on the acceleration, jerk, yaw, and yaw rates. Finally, torque is recovered from the rotational equation of motion. The key point is that torque depends on the fourth derivative of position, which is called snap. Therefore, to avoid discontinuous torque commands, the trajectory should be continuous up to snap. This motivates our use of quintic trajectory with C4 continuity. This slide summarizes the idea of differential flatness. From only 4 flat outputs, we can reconstruct the full quadrotor state, including position, attitude, thrust, and body rates. Therefore, we do not need to directly optimize the full nonlinear dynamics during planning. Now, I'll explain the overall trajectory generation pipeline. First, we represent the 3D environment as a voxel map. Then we compute the sign distance field, or SDF, which gives the distance to the nearest obstacle. Next, A-star search finds an initial collision-free geometric path. This path is converted into a fully constrained quintic trajectory. Finally, Newton-based optimization improves the trajectory by considering smoothness, obstacle clearance, and reference tracking. First, let us focus on the A-star path search step in the pipeline. So A star is used for global geometric planning in the voxel map. Each free voxel is treated as a graph node, and A star searches from the start position to the goal position by minimizing the sum of the travel cost and the heuristic distance to the goal. The output is collision free, but it is only a geometric path. It does not contain timing, velocity, acceleration, or control input information. Therefore, we use it only as an initial path before trajectory generation. Next, we convert the A star path into a fully constrained quintic trajectory. A path only tells us where to go, but a trajectory tells us where the quadrotor should be at each time. To create this, each segment between two waypoints is represented by a fifth-order polynomial. Since the polynomial is differentiable, we can compute velocity, acceleration, jerk, and snap. At each internal waypoint, we enforce the continuity of these derivatives. This C4 continuity is important because, as shown in earlier, quadrotor torque depends on the snap. After generating the initial trajectory, we apply Newton-based optimization. The optimization variables are the internal waypoint positions and the segment durations. The start and goal points are fixed. For each candidate solution, we rebuild the quintic trajectory and evaluate the total cost. The cost has three terms. The smoothness cost penalizes aggressive motion using jerk. The obstacle clearance cost uses the SDF to penalize points that are too close to obstacles. The reference cost prevents the optimized trajectory from moving too far away from the original A star path. In our implementation, we use the LBFGSB solver. The smoothness weight is 0.0006, the obstacle weight is 3, and the reference weight is 0.08. The maximum number of iteration is 28, the line search limit is 12, and the stopping tolerance is 10 to the power of minus 5. This slide shows the generated trajectory after optimization. The optimizer reduces the total cost significantly and removes the initial collision samples. In the 3D visualization, the optimized trajectory passes between obstacles while maintaining a smooth curve. This shows that the method can produce a collision-free and dynamically feasible trajectory. In this slide, we can see the generated trajectory more clearly. The optimized waypoints and the continuous curve are connected smoothly in 3D space. The important point is that the output is not just a path, but a time parameterized trajectory that the quadrotor can actually follow. Next, we compare different path search methods. We tested A star, RRT, RT star, and trapezoidal sweep in different environments, including empty, cylinder, cube, and Perlian noise maps. All methods were able to reach the goal, but the shortest path and fastest planar depended on the environment. This shows that the front-end planar should be selected based on the map structure and computation requirements. We also compare the different trajectory representations. Cubic trajectories only provide C2 continuity, so angular velocity becomes discontinuous at each notch, which leads to impulsive torque demand. In contrast, quintic trajectories provide C4 continuity, which is enough to keep the recovered torque command continuous. Therefore, we choose quintic trajectories as the minimum sufficient representation of quadrotor planning. And of course, septic is providing C6 continuity, so it satisfies the condition that I've mentioned before. That concludes our presentation, and thank you for listening.